least 2,000 years old, 2,000 plus, and we know that there had to be more than one of these things.
Yes, human beings were working on creating this geared and cogged machinery that reflected the patterns in the sky.
Oh, is that a recreation of it?
That's a recreation of something like it, yeah.
What divers pulled from the Aegean Sea looked like nothing more than scrap. A broken bronze box buried in corrosion. But inside those ruined gears was a system that didn't just track eclipses. It marked the exact moments when leaders could influence crowds and shape events.
It has been determined that that analog computer was used to predict astronomical events.
Most of the device was lost to the sea, yet the surviving pieces let researchers rebuild its full design.
They use high-resolution surface scanning, and they also use a computed X-ray tomography to get closer looks on the inside.
So who brought it back? And what did the restored machine actually reveal?
The Antikythera mechanism didn't just time travel. It is the time machine.
How divers found the first ancient computer. In the spring of 1900, a crew from the island of Symi was sailing through the Aegean toward sponge grounds off North Africa when a storm forced them to shelter near a rocky island between Crete and the Peloponnese called Antikythera. While they waited for calmer winds, they sent divers down to look for sponges. The men wore the standard gear of that time: heavy canvas suits, copper helmets, and lead-soled boots that let them walk along the bottom at around 140 feet. One diver, Elias Stadiatis, went down first. When the crew hauled him back up, he was shaken. He said the seabed was covered with dead bodies and horses scattered over the rocks, as if a whole crowd had drowned together. Captain Dimitrios Kontos thought his eyes were playing tricks on him because the water was so deep, so he suited up and went down himself. What he found was not a graveyard in the normal sense. The bodies were life-size bronze and marble statues lying on their sides or half buried in the sand, with arms, legs, and faces sticking out of the rubble. When Kontos came back up, he was holding the bronze arm of a statue. That arm was the first proof that they had stumbled onto a very rich ancient shipwreck, not just another sponge patch. News reached the Greek authorities, and soon the sponge crew was working with the Royal Hellenic Navy. For months, they risked their lives in deep, cold water to pull heavy objects off the seabed. One diver, Georgos Kritikos, died from decompression sickness, and at least 2 others were left paralyzed. The work finally stopped in 1901, not because the wreck was empty, but because the human cost was too high. Even so, they had already brought up enough finds to fill rooms in the National Archaeological Museum in Athens. The ship turned out to be a large cargo vessel from the 1st century BC, probably heading from the rich cities of the eastern Mediterranean toward Italy. Its cargo was luxury art and high-end goods. The divers lifted marble statues of heroes and gods, a famous bronze figure now called the Youth of Antikythera, a bronze philosopher's head, fine glassware, jewelry, coins, and piles of pottery. Every object they raised, from the largest statue to the smallest shard, went to Athens. Museum workers unpacked the crates and began to sort the finds. Mixed in with the marble torsos, bronze hands, and clay jars was something that did not look like art at all: a lump of corroded bronze and rotted wood, badly broken. It looked so much like scrap metal that the staff simply registered it, put a number on it, and set it aside. That forgotten lump might have stayed that way if not for an archaeologist named Valerios Steis. In 1902, while he was examining the corroded pieces, he noticed that one broken plate of bronze had a small gear wheel buried inside it. He could also see faint Greek letters scratched into the metal. At first glance, it made no sense. Gears and fine writing were not what anyone expected to find on a ship full of statues and luxury goods from more than 2,000 years ago. As conservators cleaned and studied the lump, they realized it was not one solid object but many. The corroded mass gradually split into separate chunks. Today there are about 82 known fragments, though only a few hold most of the gears. When researchers laid the parts out and compared them, they could see that they had once formed a single compact mechanism with interlocking bronze wheels, axles, and pointers. From the style of the lettering, and from other finds in the wreck, the device was dated to around the 2nd century BC, even though the ship itself likely went down closer to 60 or 50 BC, based on coins recovered from the wreck. The strange machine soon received a name, the Antikythera mechanism, after the island where it was found. Even before anyone knew exactly what it did, it was clear this was not a simple tool. Early guesses were that it might be an advanced starfinder, a special kind of navigational aid, or a unique clock. But every new look at the fragments showed that the gears inside were doing something far more complicated than any normal ship's instrument would ever need. Decades later, the work of a historian of science named Derek de Sola Price pushed things further. In the 1950s and 1960s, he spent years studying the fragments and taking X-ray pictures of the metal to see the hidden gear teeth. In 1974, he published a detailed study called Gears from the Greeks, arguing that the Antikythera mechanism was a kind of hand-cranked mechanical computer built to follow the movements of the sun and moon through time and to keep track of repeating patterns in the sky and in the calendar. After this shipwreck, the world went more than 1,000 years without making anything this mechanically advanced again. As far as the evidence shows, someone in the Greek world of the 2nd or 1st century BC built a compact machine linking the sky to turning gears, and then that level of technology disappears. Another unsettling fact is how much of the device is missing. From the broken edges and the pattern of teeth, experts estimate that only about 1/3 of the original mechanism survives. The main surviving block holds much of what used to be the back of the machine. The entire front face, where the most eye-catching display would have been, is either badly damaged or completely gone. Before anyone could rebuild the missing parts, they had to find a way to see through the corrosion, make the bronze readable again, and learn what this machine was really built to do. The scans that exposed the machine's secrets. In the early 2000s, Greek researchers teamed up with scientists from Britain and several other countries to form what became known as the Antikythera Mechanism Research Project. Their idea was simple but bold. If the human eye could not read through the corrosion, then high-tech scanners and advanced photography would have to do it instead. The big turning point came in the autumn of 2005. A British company called X-Tech Systems shipped a custom X-ray machine to the National Archaeological Museum in Athens. The device weighed about 8 tons, well over 16,000 pounds, and the team nicknamed it Blade Runner. It was built to inspect tiny cracks in jet engine parts, but here it was rolled into a museum to look inside a corroded Greek relic. Blade Runner used a kind of scan called computed tomography, or CT for short. Instead of taking a single X-ray from the front, it fired high-energy X-rays through each fragment from many angles and recorded thousands of thin slices through the metal. A computer then stacked those slices into a three-dimensional picture of what was hidden inside. Without touching the fragile bronze, the team could see buried gears, axles, and layers of writing trapped under the surface. The scans were sharp enough to pick up details smaller than 1/10 of a millimeter, finer than a grain of sand. X-rays were only half of the plan. At the same time, engineers from Hewlett-Packard brought in another tool, a special photography rig often called the PTM or RTI dome. It took many photos of each fragment while shining light from dozens of different directions. Later, on a computer screen, researchers could move a virtual light across the surface, and faint letters would pop into view as the shadows changed. Scratches that had looked random in normal light suddenly lined up into neat Greek words. Together, Connecticut scans and this relighting trick turned the mechanism into a digital puzzle. The team ended up with more than 1,000 gigabytes of data, radiographs, three-dimensional X-ray slices, and interactive surface images for every one of the 82 known fragments.
After they were able to finish their thousands of scans of the 82 pieces, something truly amazing emerges, and that is they find writing.
Over the next years, experts in ancient Greek writing sat with these images on screen, zooming in on tiny curves and dots that no one had seen clearly since the machine sank. By around 2016, they had read roughly 3,400 characters of text that had once been invisible under corrosion. Those letters turned out to be dense notes explaining what the dials did and how the machine should be set up. The writing showed that the back of the mechanism carried a kind of master calendar. Two big spiral dials on the rear face were the heart of it. The upper spiral marked a cycle of 235 lunar months, roughly 19 years, known today as the Metonic cycle. This is the amount of time it takes for the phases of the moon to fall on the same days of the solar year again. That makes it perfect for building a calendar that keeps the moon and the seasons in sync. Below it, another spiral dial tracked 223 lunar months, about 18 years, a cycle now called the Saros. This cycle is famous because eclipses repeat on it. If an eclipse happens in 1 month of the Saros, a similar one tends to happen again 1 Saros later, just over 18 years down the line. The small inner dial inside that spiral showed a longer 54-year cycle called the exoligmos. It helped fix timing drift so the machine could predict eclipses much more accurately. The CT images and the new readings also showed 3 smaller dials on the back. One tracked a 76-year cycle, known today as the Callippic cycle, which is a tighter version of the Metonic pattern. Another showed a 4-section games dial that listed major athletic contests, such as the Olympic Games and other big festivals, tying the sky directly to events on the ground. The last carried part of the exoligmos count. Around the Saros spiral, tiny symbols and short notes explained what kind of eclipse would occur, whether it was solar or lunar, how big it might be, and sometimes even hints about its color or visibility. Once the back was better understood, the team turned to the plates that once closed the case like doors. CT slices and relighting showed that these surfaces were covered in close-packed text. They read like the front page of a user manual. The sentences listed dials, pointers, and cycles. They described what each scale showed and how different parts of the machine related to one another. The language talked about periods, revolutions, and ratios. It spoke of what happens after so many months or so many turns of a pointer. Inside those same texts were clues about the front of the machine. Some lines referred to the sun, the moon, and the wandering stars, meaning the 5 planets known in ancient times: Mercury, Venus, Mars, Jupiter, and Saturn. Other passages gave numbers that matched the known cycles of these bodies, such as how long it takes Venus to return to the same position in the sky as seen from Earth. There were also month names from a type of calendar used in the Greek world around places like Epirus and Corcyra. Some parts of the writing refer to a star calendar, a list of when certain bright stars rise or set at dawn or dusk during the year. These star events, called a parapegma by modern scholars, helped people know when seasons were changing and when certain activities were due. The fact that such notes appear right on the plates of the mechanism tells us that whoever used it wanted a complete guide to the sky: the moon, the sun, the planets, eclipses, and the recurring pattern of the stars. Even with all this progress, the writing was still broken in many places. Some letters were missing. Some words had been chipped away or covered by later corrosion. To deal with gaps like these across many ancient Greek texts, another group of researchers built a machine learning model called Ithaca. It is an artificial intelligence system trained on tens of thousands of real inscriptions. When given a damaged line, it suggests which letters might be missing. Reading those texts was one thing. Turning them into a real machine was something else. The whole design had to fit inside a case not much bigger than a shoebox, and it still had to run every one of those cycles when someone turned a single crank. Rebuilding the world's first computer. The whole thing once sat inside a box about 13 inches tall, 7 inches wide, and a bit over 3 inches deep. Any honest rebuild has to play by very strict rules. The gear tooth counts seen in modern scans cannot be changed. The shafts have to line up with the actual holes and stubs still visible in the metal. The layout has to fit inside that small bronze box, not in some giant model on a lab table. And above all, whatever design you pick has to match the long cycles that the texts describe for the sun, the moon, eclipses, and the calendar. If a model fails any one of those tests, it is wrong, no matter how clever it looks. One of the first people who really tried to meet all those demands in hardware was Michael T. Wright, a curator at the Science Museum in London. In the 1990s and early 2000s, he spent years measuring the fragments, building three-dimensional drawings, and then cutting his own gears by hand. He was convinced that the missing front of the mechanism had once shown not only the sun and moon, but also the 5 visible planets, and that the only way to test that idea was to build a working copy and see if it could run. Wright's big insight was that simple, flat gear trains were not enough. To copy the strange way the moon and planets move in the sky, you need parts that do not turn at a steady speed. He used gears on gears mounted so that a smaller gear rides around a larger one, and he also used what is called a pin and slot system. In that setup, one gear carries a small pin, and that pin slides inside a curved slot in another gear. Because the pin sits closer to the center at some points and closer to the edge at others, the second gear speeds up and slows down in a smooth wave as the first gear turns. It is a very neat way to build a changing speed into a solid block of metal. Using these tricks, Wright built a brass reconstruction where the front carried rings and pointers for the known planets. When he turned the handle, the pointers looped forward and backward in a way that matched the retrograde paths ancient observers had recorded, where planets seemed to pause and move the wrong way for a while before going forward again. Some parts of his layout were still guesses, and later research has changed several areas of his design. But his models proved something important. A full front display was completely possible. The fragments we have could, in principle, support a compact machine that showed the movements of the entire sky. A new generation picked up from there. In 2021, a group at University College London led by Tony Freeth published what they called a model of the cosmos for the Antikythera mechanism. They started with everything that was now known: the exact gear counts, the size and shape of every surviving piece, and the long list of cycles and dials spelled out in the Greek text. Then they gave themselves a tough job. Every pointer mentioned in the text had to be linked to a real gear train. The entire system had to fit inside a case the same size as the original. And the timing of every part of the model had to match what we know about how the sun, moon, and planets move. They used computer models to try many different layouts, but they did not allow themselves to cheat. They could not slice away awkward gears or move fragments just to make space. In the end, their solution used 69 bronze gears in total. 35 of those matched the gearwork already known from the back of the machine and from earlier studies. The other 34 are new gears placed on the front, added to drive the sun, moon, and planets in a way that fits all the surviving clues. Packing all of that into a box about 13 inches tall is where the design gets really clever. At the core sits a main 4-spoke drive wheel turned by a handle on the side of the case. From that central wheel, thin gear trains climb upward like a small metal tower. Instead of giving each hand its own separate axle, the team used a stack of hollow tubes running through the front of the device. Each tube can spin independently and carries one pointer on the front dial. One tube turns the sun marker, another turns the moon pointer, and others are used for each planet. All of them are driven from the same main crank, but each one moves at its own speed. To save space, some of the gear trains pull double duty. A pair of gears might be part of the path that moves the sun marker and at the same time help feed motion into the chain that drives Saturn. By letting the same wheels serve more than one purpose, the ancient designer cut down the total number of parts and kept the whole mechanism thin enough to fit inside its wooden and bronze shell. The new model also gave solid homes to fragments that had puzzled people for years. One small piece, known as Fragment D, carries a gear with 63 teeth and traces of a metal disc attached to it. In the UCL model, this gear becomes part of the train that moves the marker for Venus. Its size and the way it fits against a bearing on one of the main wheels match both the physical fragment and the cycle time that the text gives for that planet. Another part, called Spoke B, fits well as a piece of the system that tracks the points where the Moon's path crosses the Sun's path. Those points decide when eclipses are possible, so this placement makes sense both for the gears and for the sky. Scientists now had a design that could make sense of the fragments, obey the math, and fit inside a box about the size of a shoebox. The final step was the one that would bring the whole story back to life, to put a hand on the crank of a rebuilt mechanism and see what appears on those crowded dials when the ancient sky starts to move again. When the machine finally comes to life, at the heart of the Antikythera mechanism's front face sits a tiny raised dome that stands in for Earth. Wrapped around it is a pointer that shows where the Moon is as it moves through the belt of zodiac constellations. Fixed to that moon pointer is a little ball about the size of a marble, painted dark on one side and light on the other. As the gears turn, that ball slowly spins. When the dark side faces forward, it shows a new moon. When the bright side faces forward, it shows a full moon. Every stage in between plays across that tiny sphere as the days pass. But the moon is only one part of the show. Around the center, thin rings are stacked like nested hoops. Each one carries one of the moving bodies that Greek astronomers watched most closely. One ring is for the moon, one for Mercury, one for Venus, one for the Sun, and then Mars, Jupiter, and Saturn. Outside all of these sits a wide ring for the zodiac, split into 12 signs. Around that, on the very edge, is a calendar band that marks out the days of the year. Each planet is marked by a small bead on its own ring. The Sun is given a special golden bead with its own pointer. The Moon is the most active of them, so it makes sense to start there. The Moon pointer shows exactly where the Moon lies along the zodiac at any given time, so you can see which constellation it sits in on a chosen night. By comparing the Moon's position to the Sun's position on the same dial, the machine also lets you read the Moon's age, meaning how many days have passed since the last new moon. The gap in days between the Sun and Moon on the dial tells you that number. The Sun's role is just as important. Its golden bead travels slowly around the zodiac ring as the year rolls on. When it crosses the first degree of Aries, that marks the start of spring. When it reaches Cancer, that is the summer solstice. When it stands in Capricorn, it is the winter solstice. When it passes through Libra, it is the fall equinox. Each planet has its own story written into its ring. The rings carry marks for events such as conjunctions, when a planet disappears in the Sun's light; oppositions, when an outer planet is opposite the Sun in the sky and rises as the Sun sets; greatest elongations, when Mercury or Venus are as far from the Sun as they ever appear in the morning or evening sky; and stations, the points where planets seem to stop briefly before they begin drifting backward against the stars. There is also a special hand moving across the dial that does not carry a planet at all. It is a long winding pointer sometimes called the dragon hand. It tracks the Moon's nodes, which are the two places where the Moon's orbit crosses the Sun's path. In many old stories, people said a dragon caused eclipses by swallowing the Sun. On the dial, the dragon hand moves slowly across the zodiac. When it slides under the Sun's bead and enters one of the marked triangles, it shows that an eclipse season has begun. Eclipses can only take place when the Sun is close to these crossing points, which happens about twice a year, and those times are flagged right on the face. So how would someone actually work the mechanism in practice? First, you set the date ring so the calendar and zodiac are aligned correctly. Then you turn the handle forward until the date ring reaches the day you want to study. Now you read the front. The golden bead shows where the Sun is. The Moon's little ball shows its phase. The Moon's pointer gives its position in the zodiac. Each planet's bead shows where it is among the signs, and the nearby markers tell you whether it is at conjunction, opposition, station, or greatest elongation. If the dragon hand lies under the Sun within one of the triangles, it means an eclipse season is underway. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.